Hey, good morning, everybody. This is Mr. Ainsworth, and we're going to get into a few more examples here on how to solve problems using what's called linear programming, invented by George Dantzig. He's the co-founder and inventor of linear programming back in the 1940s. In my first part here, I solved examples 1, 2, and 3. So today we're going to take a look at 4 on, see how many we can get through here. So let's turn the pages here and let's go to example 4. Okay, like I said, we did examples 1, 2, and 3 already. So in this video, I'd like to take a look at 4 on, and let's solve a making crafts problem here, okay? So let's read it first to get a general idea of the LP problem, okay? LP, linear programming. So here we go. Two artists, Bailey and Chloe, make ornaments. They could be you, okay? They get $80 for each wooden snowman and $64 for each wooden Santa Claus, excuse me. On average, Bailey must work 4 hours and Chloe 2 hours to make a snowman. See, that's the work time it takes to make a snowman. Bailey must work 3 hours and Chloe must work 4 hours to make Santa Claus. Okay, there's different work times to make the different toys. Okay, so these guys are kind of like elves. Okay, and they're going to be making toys for Christmas. If neither wishes to work more than 20 hours per week, okay, there's a constraint right there. No more than 20 hours per week each. That's an inequality in your mind. How many snowmen and how many Santas should they make? All right, there's your question. So let's underline that. How many should they make of each to maximize their income? So we want to formulate an appropriate linear programming problem to maximize your income. There's your goal. All right. So we want to figure out how many Santas and how many snowmen to make of each. So let's define our variables first. Okay. So let's let x equal, come on, got to start writing here. X is equal to the number of snowmen, and let y equal the number of Santa Clauses that we're going to be making here. So let's define our unknowns, and then we could fill out the table here and organize our information. So x is equal to the number of snowmen. Look right here, and then also look right here. So number of snowmen, and y is going to be equal to the number of Santa Clauses, okay? Because we're elves. It's Christmas time. Perfect time for this lesson. Okay, so let's reread the problem and organize our information. Okay, they get $80 for each wooden snowman. So $80 for the snowman, and then $64 for the Santa Claus. Okay, $64 for the Santa Claus. So that's the income made. So I'm going to fill out the income first. So right here, $80 for snowman for each one. So $80 per snowman and $64 for Santa Claus. Santa Claus. Okay, there we go. And let me see. Certain takes each L for each person, Bailey and Chloe, a certain amount of time to make each. So what we do is we go ahead and read it and fill out the table here. So for the snowman, let's talk about that first. Bailey is 4 hours and Chloe 2 hours to make a snowman. That's my first piece of information I know about. So let me highlight it. Bailey must work 4 hours and Chloe 2 hours for the snowman. So 4 hours here and 2 hours here. All right, for Bailey's 4, Chloe's 2 for the snowman. It's different for the Santa Claus. Bailey must work 3 hours. Let me check to see if that's 3. Yes, it is. 3 hours and Chloe 4 hours to make Santa Claus. So here, 3 hours for Bailey, excuse me, and Chloe 4 hours here to make the Santa Claus. Now, what's the time available? Well, if neither wishes to work more than, okay, the word neither is important, more than 20 hours, that means 20 hours or less. Okay, they do not want to work more than 20 hours. So that means the available time, all right, available time right here is less than or equal to 20 for each. It says neither wants to work more than. So if you don't want to work more than, then you want to work 20 or less. So make sure you use the inequalities properly right there. Find their maximum income. You know, how many should they make of each to maximize their income? There is the goal. So let's go ahead and interpret here and form a system of constraints and limitations, because we have a limitation on Bailey's time and a limitation on Chloe's time as well. So we have 2 constraints here that we have to start off with. So Bailey's time and Chloe's time. Those are the first two initial constraints. Okay, so Bailey's time, if she takes 4 hours for the snowman, then her total time for the snowman would be 4 times x. You want to multiply the quantity times the quantity of time per snowman times the number of snowmen. And if you're making x snowmans, you're going to have 4x hours total for Bailey. And then 2x hours here for Chloe. We'll get to that in a minute. But for Bailey, it's 4x hours for the snowman, and then 3y hours for the Santa Claus, and that's got to be less than or equal to 20 total hours. So we need to make a time constraint. So 4 hours times the number of snowmen plus 3 hours times the number of Santa Clauses has got to be less than or equal to 20 total hours for Bailey. So 4x plus 3y is less than or equal to 20 for Bailey. Now, for Bailey, it's going to be a little bit different. I got 2 hours for Chloe. Excuse me, Chloe's going to be different. Chloe's going to be 2 hours times the number of snowmen plus 4 hours right here, 4 hours times the number of Santa Claus. So 2 times x plus 4 times y has got to be less than or equal to 20. Now, since x and y stand for snowmen and Santa Clauses, they can't be negative. So my additional constraints are called non-negative constraints. And so x can't be negative, so it's got to be greater than or equal to 0. And y can't be negative, so it's got to be greater than or equal to 0. So we have to graph these 4 constraints to maximize our income. All right, so let's write an income function here. So we're going to take the income, bring it down here. Our goal is to maximize the income. So I need to write an income function. So our income, the amount of money that we're making from both of these as we produce them, would be the money that we're making per snowman times how many we're making. So I got to take 80 and multiply it by x plus 64 and multiply it by y, because that's how many I'm making of the Santa Clauses, and that will give me the total income. The question is what combination of snowmen and Santa Clauses will create the maximum income? Okay, so from here, what we want to do is graph the constraints one at a time. When I say constraint, I'm talking about these inequalities. You got to remember the constraint limitation. These are inequalities in linear programming. So over here in the margin here, we're going to take each one. We're going to isolate y and get it in slope-intercept form like we did all the other examples. So I'm going to take 4x plus 3y is less than or equal to 20. I'm going to isolate y, so I'm going to subtract 4x. I get 3y is less than or equal to negative 4x plus 20. Divide everything through by 3. Okay, and I get y is less than or equal to negative 4/3 x plus 6 2/3. 20 divided by 3 is 6 2/3. Okay. Okay, so let's graph that inequality as we go here. So I had to pause there for a second, so I apologize for that. So here we go. We're going to graph 6 2/3 first. So that's 2, 4, 6, 7, and 8. So 6 2/3 is, you divide that unit up into 3 equal parts, and you go 6 2/3 up. And then down 4, right 3. We're going to go down 4, right 3. So down 1, 2, 3, 4. 1, 2, 3 to the right. And down 1, 2, 3, 4. And then continue there. Let me see. 1, 2, 3, 4. 1, 2, 3. So it's right about here somewhere. So let's get out your straight edge here and approximate that. There we go. Now it is, I see right here that it's less than or equal to, so it's solid and below. So we're going to graph below. We're going to label this number 1, okay? Inequality 2. take the second one here. It's going to be a little bit easier. 2x plus 4y is less than or equal to 20. Going to subtract 2x. You get 4y is less than or equal to negative 2x plus 20. Divide everything through by 4. And y is less than or equal to negative 1/2 x plus 5. This one is a little bit easier. Okay, so on this one, I'm going to switch to blue. I'm going to graph the y-intercept here first at 5. Right there. All right, I'm going to go down 1, right 2. So down 1, right 2. Ooh, I just hit the other line. There's my intersection right there. Down 1, right 2. Down 1, right 2. Repeat it. And you should intersect the x-axis here at 10. So go ahead and graph the second inequality here. Let me be a little more accurate than that. There we go. Okay, and this one's below. This is number 2. So it's below both of these lines. And then the non-negative constraints right here, x greater than or equal to 0. This is your vertical boundary line. This puts you in the first quadrant, as I keep saying. X greater than or equal to 0 lies to the right of the y-axis here. It puts you to the right. So if we're going to graph the boundary line, there's what it looks like in red, x greater than or equal to 0. Let me switch to green. Okay, this is horizontal. And all y values that are greater than or equal to 0 are above the x-axis. Okay, they're up, they're above. Because below the y-axis, well, they're negative, right? So y greater than or equal to 0 is horizontal. So this one's horizontal and up. So where does the red, the blue, and the black, all these colors, all these regions overlap? Okay, well, it's in this little bounded region right through here. This is your feasible region right here. And it's a quadrilateral, so it has 4 vertices. So your feasible region, or your solution region, however you want to say it, has 4 vertices right here. Okay, and we'll call that point A at 0, 5. There's my first intersection point, or excuse me, my first vertex. My second vertex at B here, and that's right 2 up 1, 2, 3, 4. So B is at 2, 4. And C is right here at, let me see, C, it's right 1, 2, 3, 4, 5. So 5, 0. And of course, we've got the origin here, D, which we're not going to pick, but we're going to label it anyways, 0, 0. Okay, we want to make something, so we're not going to pick D, but we're going to list it out because it is a vertex. Okay, so now, which one produces the maximum income? So let's go ahead and solve the problem. So the income, I, is 80 times the number of whatever x is, and that stands for, let's review here. X is snowman and y is Santa Claus. Okay, so here we go. So this is snowman here, snowman. Okay, and this is Santa Claus. Y is Santa Claus. So how many of each should we make to maximize the income? So 80x plus 64y. So let's take each vertex. A is right here, 0, 5. B at 2, 4. C at 5, 0. And our non-solution, which is a solution, is D. So what's the income for each? So 80 times 0. Remember, this is x and this is y. Plus 64 times 5. Okay, that produces, let me see, 64 times is 320, so 320 bucks. For the second one, it's 80 times 2 plus 64 times 4. Remember, this is x and this is y each time. So let me see, it's 160 plus 1, let me see, 60 times 4 is 240 plus 16, 256, so 256. And if you add these guys, you get 410 plus 6, 416. Ooh, more money. 416 bucks there. On this one here, we've got 80 times 5 plus 0. Let me see, so that's 400, not as much income. And then here, this is going to produce 0, right? 80 times 0 plus 64 times 0. Well, that's 0. So my maximum income that I see is right here at point B. So we have to interpret, what's the best solution? What's the optimal solution? So we should make, Okay, we or Chloe, actually Chloe, let's say it correctly here. Chloe and Bailey. Chloe and Bailey. So those are the names. Let's see here. Yeah, Bailey and Chloe. So Bailey and Chloe should make, all right, two right here. Remember, X is snowmen. So 2 snowmen and 4 Santa Clauses should make 2 snowmen. All right, and 4 Santa Clauses. Santa Clauses, all right, to maximize their income. Okay, which in this case is $416. All right, so they want to make the most money because that's what people do in business. All right, they want to make money. And so if you were doing this and you had these constraints, then this would be the optimal solution. All right, given the problem here. So you got to use the video effectively here. So if I went a little bit too fast, all right, why don't you pause the video, rewind it, and use it to your advantage. And you can listen to this any part over and over again you want until you understand the problem fully, until you can do it on your own. All right, because you know I go different speeds than you guys, and then that's okay. Just use your video effectively and properly, and use it to your advantage. All right, I always send these guys out to you, or I put them on my website. All right, so that's how you solve this problem here. We'll call it a making crafts problem here, dealing with ornaments, all right, during Christmas time. Now, what you guys need to do is try something new. So on the next page, number 5. Number 5. How do you do number 5? Number 5 is the diet problem. Ooh. The diet problem is cool because, you know, this is a real problem and it's different here because this time you want to minimize something instead of maximize something. So let's read the problem here and let's get it set up. So a diet requires at least 16 units. Ooh, at least 16 units of vitamin C. So that's one constraint. And then the other one right here, at least 34 units of vitamin B complex. All right, to be healthy here. So you got to interpret these at least 16. At the words at least, really, really important words right here. You have to interpret that as greater than or equal to 16. And then this one, at least 34, is greater than or equal to 34. These are constraints on the problem. You need this to make this happen to be healthy. Okay, 2 food supplements are available that provide nutrients in that amounts, and the costs are shown in the table. How much of each should be used to maximize the cost? Ooh, how much of each? So let's highlight the problem here. How much should be used of the supplements? I'm not talking about vitamin B and C. I'm talking about the supplements right here to make sure you have enough vitamin C in your diet and vitamin B. All right, so there lies the variables here. So how much of each supplement? Okay, supplement. So let's X equal the number of grams here. The units are in grams, as you can tell. So number of grams of supplement A. And then let's let Y equal the number of grams of supplement B. So the question is, how much of each supplement should we take to make sure we have a healthy diet? Enough vitamin C and enough vitamin B in our diet, you know, at least 16 units of vitamin C and at least 34 units of vitamin B. So how much should you take of each to make that happen? Okay. So let's interpret here. We want at least 16 units of vitamin C. So look at the vitamin C category right here. And let's put that inequality in. We've got to have our minimum amount is 16. So it's greater than or equal to 16. Notice minimum amounts here. And for vitamin B, well, that's you need a little bit more. So that's a little bit different right here. So right here on our vitamin B is greater than or equal to 34 units. Okay, whatever that unit is. Okay, of measurement. Now they cost different amounts too. Notice in the table, each costs differently. So supplement A costs 3 cents per gram and supplement B costs 4 cents per gram. So there's a cost involved. All right, so the question is, how much should you take of each to minimize the cost? All right, you want to minimize the cost in this one while maintaining a healthy diet because you don't want to spend too much. So we have to write a cost function. So the cost on each one of these, let me see, if there's 3 cents for every gram, we got 3 times, the number of grams, which is x. So we got to take your 3 here and multiply it by the number of grams. So 3 times x, let me label this better, cost equals 3 times however many grams used of supplement A times 4 cents, look right here, 4 cents times however many grams of supplement B, so plus 4 times y. And that's going to be in dollars, of course, or excuse me, cents. So cents. So the question is how much should you use of each supplement to minimize the cost? So let's interpret. All right, we'll keep interpreting here. Let's write down our variables first as we did up here. So X stands for the number of grams of sup A, okay? Number of grams of supplement A. And Y equals the number of grams of supplement B. Okay, the most common mistake people make on this problem is they think it's X and Y stand for the vitamin B and C, and that's not the case. It's just part of the supplement. Okay, so you got to be careful on that. Okay, now our constraints. We have a constraint on vitamin C. We need at least 16 units on it. So let's take our constraint here and start writing it down. So our first constraint is on vitamin C. Our second constraint is on vitamin B. We'll do that in a minute. So look vertically now. Okay, this is organized a little bit differently than our last problem. So for every gram of supplement A, we got 3 units of per gram of vitamin C inside of it. So we got to take 3 times whatever X is plus 2 units per gram times whatever Y is. So 3 times X plus 2 times Y, that's got to be greater than or equal to 16 units to have a healthy diet. You want to have at least 16 units of C in it. So you take the units per gram, how much vitamin C is inside each gram of sup A, okay? Multiply 3 times X and then 2 times Y, and that's got to be greater than or equal to 16. So 3 times X plus 2 times Y, and that's greater than or equal to 16. Our next constraint is here. For every gram of sup A, we have 2 units of vitamin B inside, and 6 units of vitamin B inside supplement B. So vitamin or supplement B is much richer in vitamin B than supplement A. Okay, it's much richer in that. So the question is, how much should we use? So you take 2 times X plus 6 times Y. It's got to be greater than or equal to 34 this time because you want at least 34 units of vitamin B in your diet. So 2 times X plus 6 times Y is got to be greater than or equal to 34. Okay. Now, our objective is to minimize the cost. So let's write our cost function down here. We want to minimize cost. So our cost function, C, looks like 3 cents times X and 4 cents times Y. So 3X plus 4Y. And that's in cents, not dollars. So let me change that. Okay. So we want to minimize that. The question is, what are the corner points in this linear programming problem? So let's write down our non-negative constraints here. Okay, X can't be greater. X has to be positive or 0. Y has to be positive or 0. They can't be negative, right? You can't have a negative grams of supplement A or B. It doesn't make any sense. So they got to be positive or 0. We call that non-negative. Sorry about that. So we got to continue here, and we have to isolate Y on both of these. So let's take 3X plus 2Y is greater than or equal to 16. And let's isolate Y here. Okay, so we're going to subtract 3x. And you get 2y is greater than or equal to negative 3x plus 16. Dividing everything by 2, you have y greater than or equal to negative 3 halves x plus 8. So let's graph this here. So it's 2, 4, 6, 8. Let's plot here. Okay, so let's graph this inequality here now that I'm back. Sorry for the little interruption right there. So we're going to go start at the y-intercept of 8 right here. Okay, so here we go after one more interruption here. So let me see if I can get a flow going here. We're going to start at 8 here, and we're going to go down 3, right 2 from the y-intercept. So 1, 2, 3, right 2. 1, 2, 3, right 2. 1, 2, 3, right 2, right about there. Go ahead and get your straight edge out now, and let's graph that line right about there. All right, I'm looking at the inequality now on this one here. Check this out. This right here is solid and above. All right, when it's greater than, it's always above. So solid and above. So you got to be careful on your inequalities. Let's label this number 1 here. First inequality here, first constraint. It's greater than, so you have to go above. So very, very important right there. That's what is the difference between all the previous ones and this one here, is that this is a minimization problem, and the inequalities are minimums. And then we're going to have to graph above the boundary lines and not below. Okay, so key difference between the previous examples and this one. Now, the constraint on vitamin B is 2x plus 6y greater than or equal to 34. Okay, so on this one right here, let's see here, we have y, oh no, excuse me, we have to subtract 2x here on both sides, and we get 6y greater than or equal to negative 2x plus 34. Divide everything through by 6. So y is greater than or equal to negative 1/3. You got to simplify your fraction. 6 divides into 34 5 times with 4 remaining, so it's 5 6/4. Now 5 6/4 is 5 2/3. Okay, so we're going to graph with a slope of negative 1/3 and the y-intercept of 5 2/3. I'm going to switch to blue here. So 5 2/3 is, let me see, here's 5, and 5 2/3 is between 5 and 6, obviously. 2/3 of the way up, so right about here. Okay, go down, let me see, we're going to go down 1, right 3. So put your pencil at 5 2/3 and go down 1, and then right 3. 1, 2, 3, right about here. Down 1, right 3. Down 1, right 3. Down 1, right 3. Down 1, right 3. 1, 2, 3, right about there. All right, so let's grab our straight edge out, and we go ahead and give a good, okay, good line there. So, and then once more, check this out. Right here, it's going to be solid and above again because greater than or equal to, so solid and above. Start learning how to just quickly identify how to graph your inequalities here. So we're going to go solid and above. Oh, I should continue right here. We got to go down 1, right 3. I got to continue this line. So let me continue this because we need to figure out where it intersects the x-axis here. So see, this is 10, 11, 12. This is 15, and this is 16, and then this is 17. So it should intersect at 17. Okay. So just continue that right there. And then we have our non-negative constraints. So right here, I'm going to graph x greater than or equal to 0. All x values greater than or equal to 0 to the right of the y-axis. I mean, just look at them. 1, 2, 3. All the x values are to the right. So this is inequality number 3, x greater than or equal to 0. Always vertical and to the right. So this one's in red. All right, and this one, last one's going to be in blue right here. If I can spell blue. Okay, there we go. So y greater than or equal to 0 is above the axis, above the x-axis, that is. So y greater than or equal to 0, this is inequality number 4, is above, right? All the y values like 1, 2, 3, 4, all these y values here on the y-axis are above the x-axis. Okay, remember these arrows are infinite, right? They continue going up. All the y values are positive, infinitely up. So the big question is, at this point, is where's the feasible region? Okay, is it in region 1, 2, 3, 3 right here, 4, 5, 6, way over here, 7, 7 here, 8 here. So where is it? Where does the blue and the black and the red, all these intersect? And if you take a look at all the arrows, it's got to be above this boundary line and above this boundary line and to the right of the y-axis and above the x-axis here. So it's all in through here. All right, so let's highlight this. This is a big unbounded, your first unbounded feasible region. And the reason why this occurs is because we have minimums, okay, as opposed to maximums. So get your straight edge out, excuse me, your highlighter out, and let's highlight the feasible region. There we go. All right, so here's the feasible region right here. Let's denote that. Feasible region, or solution region, as you called it initially, okay? The feasible region. And we've got to find the corners of this. And so I see one right here. So I'm going to call this point A at 0, 8. So A at 0, 8. Point B is right here. All right, and it's right 2 up 5. So B is 2, 5. And then C is right here. And that's going to be, let me see, 17, 0. Hopefully you can see that. So let me record those. So B is at 2, 5, and C is at 17, 0. All right, the origin is not part of this because it's not in the feasible region. Okay, so we want to check these 3 ordered pairs, these 3 points, these 3 corner points. All right, we're at this step right now. Using the vertices or corner points, evaluate the objective function. All right, now you got to remember on this problem, we are trying to minimize the cost. So the cost is 3 times whatever x is plus 4 times whatever y is, where x is 0 and y is 4. On the first point, that is. Okay, so we're going to take these points and we're going to substitute them in and we're going to minimize it. All right, we're going to minimize the function. You don't want to maximize cost. You don't want a lot of cost. You want a minimum cost. You want a low cost, high profit or income, and low cost. Remember that in business. So the cost here is going to be equal to, oh, these are in cents, not dollars. So let me erase that, cents. So 3 times 0 plus 4 times 8. All right, that's 32 cents. Cost here is going to be 3 times 2 plus 4 times 5. So that's 12 and 20. That's 32 cents. And here the cost here is going to be 3 times 17 plus 4 times 0. That's 51 cents. Okay, so we want to find not the biggest but the smallest. We want to minimize. We want to minimize here. And if you compare here, whoops, 32, what happened here? 4 times 5, 20. Oh, I didn't write this down correctly here. Oh, going too fast. 3 times 2 is not 12, it's 6. Okay, 6 and 20, 26 cents. So check your notes there. Hopefully you didn't make the same mistake I did. I just saw an error there. 3 times 2 is 6, 4 times 5 is 20, 20 and 6 is 26 cents. So 32, okay, compared to, let me just highlight the cost here. If you compare all these, what's the smallest? And 26 is smaller than any of these otherwise. So this is the minimum, right? And it occurs at this point right here. So to optimize, which is the best solution here, is the following. We want 2 of whatever x is and 5 of whatever y is. So let's go back up to our variables here so we can understand the problem. You always go back to your definitions and understand what it means. So x is the number of grams of supplement A. So we want 2 grams of supplement A and 5 grams of supplement B, all right, to minimize the cost. So here we go. The best solution would be to take 2 grams, or use 2 grams of supplement A and 5 grams of supplement B. All right, to minimize, to minimize cost. To minimize the cost, which in this case is going to be equal to 26 cents. Okay? This is per gram. Okay, so 26 cents. So There you go, right there. And again, this is a video, right? And I apologize for all the little interruptions right there, but you got the idea. You can go back and listen to this again. And again, the most important thing is do you understand is how to interpret the table into a system. From going table to system, that is the hardest part. All right, the system of constraints. Going from that to the graph is a little bit easier because we've done it so much. But learning how to convert and interpret, or what we say is model the problem into a system of constraints, that is the key. And that's what I want you to learn through these exercises. All right, so one last one here. Let's take a look at a scheduling problem here. Number 6. If you want to give it a shot on your own, go ahead and pause the video. But otherwise, go ahead and just keep it going. If you don't know how to do it, but personally, I would prefer you guys to pause the video and give it a shot, and then check it with me when you guys are done. Okay, that's the best way to do it. Try it first, and then check it with me. And on this one here, before you graph, this graph is really not big enough. So take out a piece of graph paper, and because you're going to need it probably, I think, and that will help you graph this situation here, because this one's a little bit different in terms of the y-intercept. So you'll see when you get there. Okay, here we go. Go for it. All right, we're back now. So let's read the problem here. A manufacturer of fiberglass camper tops for pickup trucks makes a compact model and a regular model. So a compact model is, we got two things going on here, and a regular model. Each compact top requires 5 hours of fabricating department and 2 hours in the finishing department. So we got two different departments here, fabricating and finishing. Each regular top requires 4 hours of the fabricating department and 3 hours of the finishing department. Okay, the maximum labor available. Maximum available per week in fabricating is 200 hours, and maximum labor hours in the finishing department is 108. Those are the limitations or the constraints. All right, if the company makes a profit of $40 on each compact top and $50 on each regular top, how many tops of each type? Here's the question: how many tops of each type should be manufactured to minimize the total weekly profit? That is your goal. Okay? To maximize, actually, here's your goal. This is the goal. Let's put the goal right here. All right. So how many tops of each should we manufacture or make to maximize the total weekly profit? There's your goal. All right, so let's define some unknowns, and let's fill out the table here and go for it, okay? Now, we don't know the number of each compact and regular model, so we start with a variable. So we got a compact model, we got a regular model. We're going to let x equal the number of compacts and y equal to the number of regular right here. So let's be specific when we and get organized here. Number of compact models. Y is equal to the number of regular models. That comes from my question. Okay, if it's asking me how many tops of each type, okay, compact versus regular, well, there lies the variables, right? Okay, now what we do is we reread the problem after we understand what's going on and fill out the table. Each compact top requires 5 hours of fabricating. So 5 right here hours of fabricating. So, and that's compact. So 5 hours of fabricating. And 2 hours right here of finishing. 2 hours of finishing. That's for the compact model. Then it says each regular top requires 4 hours of fabricating. So 4 hours of fabricating. And reading on, 3 hours of finishing. So 3 hours of the finishing. Okay, the maximum labor hours available, maximum. That's right here. Okay, per week for fabricating is 200 hours. Now, if it's a maximum keyword, all right, we cannot go over 2 hours. So we have to stay under, less than or equal to 200 hours because of the word maximum. If it said minimum, I'd go greater than or equal to. All right, but it says maximum. And then it says and in the 200 hours, and the maximum labor hours right here for the finishing department is 108. So maximum it's got to be less than or equal to 108 because it's maximum. So for finishing, it's less than or equal to 108 hours. For fabricating, it's less than or equal to 200 hours. Now the profits, what are the profits? Well, it says right here, the company makes a profit of $40 on each compact. All right, compact model, right? And then $50 on a regular top. Okay, those are the profits. So the big question is what's the max profit and how many of each model do you produce to maximize your profit? How do you do that? All right, so let's interpret the table into a system and solve the system. Okay, now because there's a maximum labor hours for the fabricating and the finishing, these become the constraints. Okay, so we got a constraint here and a constraint here. So the first one is your fabricating constraint. Okay, now it's 5 hours. It takes 5 hours for each compact model. So you got to multiply the number of hours for each compact model and multiply by how many you're making. So I see 5 times x plus 4 times y, and that's got to be less than or equal to 200 total hours because it says maximum. You can't go over that. Now the second constraint is for the finishing. All right, so for the finishing, for the compact model, it takes 2 hours times whatever x is. X stands for the number of compact models. So 2 times x plus 3 times y, that's got to be less than or equal to 108 hours for the finishing. Can't go over 108 hours. And that's why it's a limitation or a constraint. That's where these names come from, because you cannot go over that. It's a maximum number. Okay? So, so now you got that going on here. Your non-negative constraints, your variables cannot be negative. So x has got to be greater than or equal to 0. Y has got to be greater than or equal to 0. Okay, that right there is going to be part of most problems here because the variables can't be negative. That wouldn't make any sense. And our goal, our profit function, right here, the profit is our goal. We want to maximize profit. Max profit. So we need to write a profit function. All right, so we take $40 times the number of compact models we have. So you got to take 40, multiply it by x. So profit is equal to 40 times x. You get $40 for each compact model and the $50 for every regular model, right? So plus 50 times y. There's your profit function, and we're going to maximize that after we're done with the feasible region. Okay, so what we need to do now is graph this situation. So to do that, though, let's take each inequality like we normally do, and let's solve for y and get it in slope-intercept form. So subtract 5x. You get 4y less than or equal to negative 5x plus 200. Divide everything by 4. And you get y is less than or equal to negative 5/4 x plus 50. And notice a big y-intercept there, so it's going to be challenging. Okay. And let's see here. Next one, I'm going to solve for both of them here. 2x plus 3y is less than or equal to 108. So subtract 2x. Let's just do the arithmetic first, and then I'll decide which graph I'm going to use and what scale I'm going to use right here. Is less than or equal to negative 2x plus 108 divided by 3. Believe it or not, 108 is divisible by 3. And you get y is equal to negative 2/3 x plus 108 divided by 3. 3 into 10 is 9. Subtract, and remainder 1, bring down the 8. And then 3 into 18 divide 6 times, so it's 36. So a y-intercept is 36. So we have to graph this function here and this function here. So we'll call this inequality 1, and this is inequality number 2. We have to graph these. Now we have big y-intercepts here and here. And obviously if you keep the scale at 1, you're not going to be able to graph it. So what we're going to do, even if we change the scale to 2, we're not going to be able to graph it because we got to go all the way up to 50. So, and we got to be accurate, and that's the key on this one here. So what I want you guys to do is take out a piece of graph paper, and we're going to do this on a yeah, it'd probably be easier to do it on another piece of graph paper and choose a scale of 2. All right, so let's do that. Take out a piece of graph paper. I'm going to go to this one here. I'm going to get a graph paper myself. Let's choose this one. Set up some axes here. So get your straight edge out. Let's set up a corner plane. Let's graph. There we go. All right, and then let's write the results down over here. So inequality number 1, if you look at your notes right there, is equal to, let me get it back here, negative 5/4 x plus 50. So y is less than or equal to negative 5/4 x plus 50. And then number 2, y is less than or equal to negative 2/3 x plus 36. Negative 2/3 x plus 36. Slope, y-intercept, slope, y-intercept. So here we go. So let's see here. We're going to change the scale to 2, I think. That means we need 25 up. Let's see if I have that. So if we change the scale to 2, that's 2, 4, 6, 8. And this is 10. So this is 2, 4, and so on. I'm changing the scale to 2. So 12, 14, 16, 18, 20. So that's 20. So basically every 5 is equal to 10. So 1, 2, 3, 4, 5, 30. Yeah, this is going to work. 32, 34, 36, 38, 40. Here we go. 1, 2, 3, 4. There we go. Scale equals 2 now. Same thing on the x-axis. Okay, so count every 5. So 1, 2, 3, 4. There we go. So that's 10, 20, 30. Oop, I'm off. Don't do what I just did. 1, 2, 3, 4, 5. Count. Be accurate. Okay, so change the scale. X-axis, y-axis up here. So here we go. Now on a slope of negative 5/4, if you multiply by 2, that's the same thing as negative 10/8. Multiply by 2. So starting at 50. So starting right up here, I'm going to, instead of going down 5 right 4, I'm going to go down 10 right 8. So down 10, it's 2, 4, 6, 8, 10, down 2, 4, 6, 8 right here. Down 10, 1, 2, let me make this point a little bit bigger here. 2, 4, 6, 8, 10, 2, 4, 6, 8. And so down 10, 2, 4, 6, 8, 10, right 4, or excuse me, right 8, 2, 4, 6, 8, 2, 4, 6, 8, 10, 2, 4, 6, 8, 2, 4, 6, 8, 10, 2, 4, 6. So if we did this correctly here, oh, you know what? I messed up on my graph, so don't do what I just did. Holy cow, I can see that I messed up right here. Okay, so let me redraw the x-axis here. See, you got to be careful when you count. So every 5. There's go 20, 30, 40. Let me see, every 5, that's 50. So 2, 4, 6, 8, 10, 2, 4, 6, 8. You should intersect at 40. There we go. This is correct. So count properly is what I'm saying. You got to be very accurate. Okay, draw your inequality. Right there. I can see that it's less than or equal to right here. And so it's solid and down. So it's solid. And it's less than or equal to, so below. So we're going to graph number 1. This is inequality 1. Below. Now, the slope of negative 2/3 is the same thing if you multiply it by, let's say, 10 10 over 10, let's say. This is the same thing as a negative 20 over 30. That's probably the easiest way to do it right here. Oh, I could have done that up here. I could have said this is negative 50 over 40 and just went down 50, right 40, and boom, ended up right here. That would have been good too. All right, so down 20, right 30, starting at 36. So I'm going to do this one in blue. So starting at 36, which is right here. So down 20, right 30. So, well, actually, you know what? I'm going to multiply both of these by 2. So negative 4, 6. So down 4, right 6. So down 4, 1, 2, right 6, 1, 2, 3, right, 2, 4, 6, excuse me. Down 4, 2, 4, right 6, 2, 4, 6. Down 4, right 6. Down 4, right 6. Ooh, intersected right there. Down 4, right 6. Just keep on going. Okay, and we should have intersected right there at 54. Okay, so go ahead and draw your line right there. Your inequality, your boundary line, that is. Okay, and let's label this. This is number 2. First one's number 1. It's I can see right here it's less than or equal to, so it's solid and below. Okay, so let's go ahead and do that. So it's got to be below both of these boundary lines. Non-negative constraints, x greater than or equal to 0 is right here. It's got to be to the right of the y-axis. All x values are to the right of the, this is x greater than or equal to 0. And then the last one here, number 4, is y greater than or equal to 0. It has to be above the x-axis. Y greater than or equal to 0. Okay, and once you have all these constraints or inequalities labeled and graphed, then you find the intersection of all these regions, and it's got to be in here. Okay, they all intersect through here. This is your solution region, your feasible region. All right, these are the points that satisfy all 4 inequalities, not just one of them, but all 4. And any point in here will make it feasible to make it optimal, all right, to satisfy your problem or to optimize this problem. So what we need to do is write down the vertices, because George Dantzig, okay, found that the vertices of the feasible region are the solutions to the linear programming problem. Okay, so solutions exist here, all through here, but the best ones are A, B, C, D's we're going to list it, but it's not going to be a good one because it means we don't build anything at all. A is 0, 36. B is 24, 20. So B is 24, 20. C is 40, 0. So we have 3 vertices that we need to check and analyze. Okay, so let's go back to the our lesson here, and let's take these vertices and let's maximize the profit and finish the problem. Okay, so here we go. So finishing up now, we have A, which was 0, 36, B, which was 24, 20, C, which was 40, 0. Which one maximizes profit? So let's take this profit function here. It's 40 times whatever x is plus 50 times whatever y is, and let's figure out our profits. So for the first one, we got to take 40 times 0, and then plus 50 times 36. Now, you can use your calculator anytime, or you can do a little side arithmetic. It doesn't matter. 40 times 0 is 0, obviously, but you got to figure out what 50 times 36 is. So we're going to go 50 times 36. That's going to be 1800. So this gives a profit of 1800. Is that the best? I don't know. Let's figure it out. So 40 times 24 plus 50 times 24. Let's figure this out. So 40 times 24, that's 960. And then 50 times 24, oh, not 24, 20. That's 1,000. All right. And so that's 1960. All right. And the last one here is 40 times 40 plus 50 times 0. That's 1600. All right, so the question is which one maximizes your profit? Which one's the biggest? And obviously, it's this one right here, and it occurs when we do this right here. So what in the world is the best solution? What does X and Y mean? So we go back up to the basics here and read what X and Y refers to. Okay, X is the number of compact models, and then Y is the number of regular models. Okay, so we need to build 24 compact models. All right, and 20 regular. 20 regular models. All right, to maximize profit, which in this case, all right, turns out to be 1,960 bucks. All right, so the best solution to do this is we need to build the models in this format here, 24 compact and 20 regular, in order to obtain the maximum profit. Okay, in any business, you're trying to make the most money. All right, and in this case, we call that profit, not income. All right, in this case, and to do that, well, we just build 24 compacts and 20 regulars, and that will do the job. Anything different than that will give us a profit probably, but not as high. Okay, that's what maximizing is all about, the most. Okay, and that is 3 more examples there, guys. And this is a video, like I said, and use it to your advantage here. If I go too fast, pause it and play it, rewind it to your advantage. You have the ability to go through all 3 examples at your leisure, at home, at your own speed, okay? So do yourself a good job here, finish your work, and I will see you on next lesson here. This is Ainsworth. I'm out. Bye-bye.